Okay, this is the second part of electrochemistry. The first part was all about the theory, and the second part are practical applications of the theory. So electrochemical cells are the practical applications of the theory, which basically means producing electricity from these chemicals or using electricity to make the chemicals do unspontaneous reactions. So it's transferring electrical energy into chemical energy or chemical energy into electric energy and making that useful for us. Okay, so I want to today cover voltaic cells. So there are two kinds of electrochemical cells, voltaic cells and electrolytic cells. These voltaic cells are our spontaneous reaction. They're going to produce a voltage. It's a fancy way of saying a battery. We're going to learn what's inside a battery today. So before we get there, I just want to recall this example that we've already done when we predicted the 5-step equation. And we're going to make this become our battery today. So if you remember, we put some copper wire into a silver nitrate solution, and we said that it just magically reacted, spontaneously reacted. In order to figure out what the reaction was, we made a species list. We put our finger in our data booklet. We found that this was the strongest copper reducing agent, was this, you know what I mean? And the strongest oxidizing agent was the silver ions. And so the copper was going to give its electrons to silver ions, and the copper will become copper 2+, and the silver ions will become silver. And what you see is this fuzziness appearing on the copper wire. So there's my fuzziness appearing on the copper wire. And the silver ions become that silver. And the solution turns blue over some time because we're producing this copper 2+. This is my oxidation half reaction, that's my reduction half reaction, and this is the net redox reaction. Okay, so in the late 1700s, Alexander Voltaire was doing reactions, not quite like this. He was using like frog's legs, but that's a whole other story. But let's just pretend for today that he was doing exactly this part of the magic show. And he knew that it had something to do with, well, I didn't really know it had transfer of electrons, but he hoped it did. I don't know what he hoped. Anyway, it doesn't matter. This is magic. It just magically happens in front of you. And Alexander Voltaire was like, I want to be a part of that magic. I want to take these electrons and I want to make them useful, because up till now, like electric eels and like shocking yourself from static electricity and lightning bolts, they knew electricity existed, but they couldn't harness it yet and make it useful. So Alexander Voltaire thought, you know what, if I could just be a part of these electrons for just a second, maybe we could do something with that. If the copper, when it gives its electrons to silver, if it could just give it to me first and then give it to silver, oh man, that'd be awesome. So he thought, well, in order to do that, I'm going to have to take these two half reactions. I'm going to have to separate them. So he put them in separate containers. There's my silver ion, there's my copper. And he's like, all right, now if you want to give up your electrons to silver, you got to jump through some hoops here. And so he understood that this isn't like totally finished. I need something to connect those electrons together. So maybe a metal wire to help connect the electrons, maybe another metal stick to help connect the electrons. I'm going to make this metal stick a silver solid stick. That says Ag for silver. And I'm going to have a wire connect these two things. Okay? Now remember, Alexander Voltaire also wanted to be a part of this. So he's going to, he wants to be a part of this transfer of electrons. And he wants the copper to give its 2 electrons over to silver, and aha, nothing happened, nothing. So we thought, well, maybe the electrolytes also need to complete a circuit, because we all know flow of electricity, you have to have a full circle, right? And so he thought, well, maybe I should just put another electrolyte in here, like that, make this my copper 2+, and have some kind of pathway for those ions to travel back and forth. So he made this this is called a U-tube because it's shaped like a U. And he filled this U-tube with another electrolyte, like let's just put some table salt Oh my goodness. Soluble, dissolved. Okay, so this is filled with some NaCl aqueous. And now we can have the electrons go, we can have the ions flow if the ions want to flow, because remember, electrolytes are soluble ionic compounds that conduct electricity. So maybe that has something to do with conducting electricity too, because obviously the electrolytes have something to do with the electricity. And so now he set this whole thing up. He has the two half cells. If copper wants to give its 2 electrons over to those silver ions, they're going to have to follow this kind of a pathway in order to get and reach those silver ions, right? And so he literally took those wires and literally stuck them in his ears in hopes of being a part of this magic. And his journal entry says something like, I felt the most disagreeable sensation. I heard a snap, crackle, and pop. It was, I don't actually know if it said snap, crackle, and pop, but that's pretty funny if you did. And this sensation was so disagreeable that I decided not to repeat the experiment more than once. That's literally what his journal article was, with frog legs all over the table and whatever. But anyway, so maybe after a while he decided not to do that anymore and not put himself, maybe put a bell or something so that he could hear the electricity. Whatever, but let's put a light bulb in here because a light bulb's easier to draw than a bell. And this light bulb lit up on him. Not really, because he didn't have light bulbs yet, but whatever. For us, the light bulb would light up. This would produce a voltage. This, remember, is your battery, and the battery then can make your light bulb light up. Yeah, we've just made a battery out of essentially what we learned last chapter. So how does this relate with this? Okay, well, when you see a picture like this, you're going to go, and it asks you stuff about it. The first thing you have to do is make a species list, just like we did for those word problems on the 5-thing equation. So you're going to go, okay, species list. What have I got here? I've got copper. I've got silver ions. I probably have some nitrate here. Let's say that was silver nitrate originally, right? So nitrate, fine. I've got some sodium ions and some chloride ions from my salt bridge. I have some copper 2+ ions from this other side. Okay, there's my species list. Put your finger, find your strongest oxidizing agent. Guess what? You're going to come up with Ag1+ is still your strongest oxidizing agent. Put your finger, find your strongest reducing agent. You're going to find that copper is still your strongest reducing agent. So out of my species list, I've just added some really weak reducing agents and weak oxidizing agents. And so this is still my Leo, this is still my Gur, this is still my Net, and it's still spontaneous. The only difference between this crazy setup of glassware and this little magic show is we get to be a part of this. We can actually read how many volts this battery produces. 1.5 volt battery, 9 volt battery. It all depends on what kind of chemicals are inside that battery, but you're going to have 2 half reactions. One's an oxidation half reaction, one's a reducing half reaction, because there's a Leo and there's a Gur, there's the strongest reducing agent, there's the strongest oxidizing agent. Okay, so, right. So there is some vocabulary that comes with this, because otherwise it's too easy for a whole chapter, right? So some vocabulary that comes with this are what all these bits and pieces are called. So I made a little list here. So in here we have electrodes. Electrodes are our rods. A rod as in like a stick. So here's my first electrode and here's my second electrode. One of these electrodes is going to be called the cathode. That'll be the positive end of the battery. You know, batteries have positive end and negative end. So that'll be the positive end of the battery. And the other stick is going to be called the anode. So how do you know which is which? Well, you know how Leo, the lion, says grr, you know, that manly lion, grr, whatever. Anyway, Leo, the lioness. Leo, the lioness. Well, she says, grk. You won't forget it. I don't say that very often, but anyway. Okay, so Leo says Gurk. So therefore, if I go over here, the anode is where the oxidation half reaction happens. So who's my oxidation half reaction? Well, that's the copper. The copper is my oxidation half reaction, and so therefore the copper must be my anode because it's the loss of electrons oxidation half reaction. So, and anodes are negatively charged, so this is going to be the negative end of the battery. So the copper is my anode. The other stick then must be my cathode, but let's just talk that through. The silver is my cathode. It is positively charged. That's the positive stick of the battery. Because at the cathode, the reduction half reaction happens. That's the silver pluses gaining those electrons. So hold on a minute. Let's follow these electrons. They came out of the copper. They went through our voltmeter. They're coming down that stick. So here are my, I'll use blue just like I had last time. So here are those 2 electrons that came firing out of the copper. Remember, the copper fired out 2 electrons. So the electrons travel, electrons travel, electrons travel. They're hanging out here. This silver ion sees one of those electrons. The silver ion sees one of those electrons, picks it up, and becomes silver solid, right? So the silver solid then forms on top of the, like it just kind of sticks to the metal, just like it did over here, sticks to the metal, makes that shiny layer on the outside. So I produced my silver. So anyway, what I was saying is the cathode is the site of the reduction. There's the site of the reduction. And so this stick is my cathode because cathodes are rods, sticks. Okay. So rods, sticks, anodes, cathodes. Okay, now the electrons always travel from the anode to the cathode through the wire. The electrons travel from the anode to the cathode through the wire. Let's follow that. They traveled from the anode, oh yeah, because the copper gave away its 2 electrons, to the cathode, oh, here we go, through the wire. Okay, got it. Next bit of vocabulary, electrolyte. I already defined that as the soluble ionic compound that conducts electricity. Electrolytes by definition can also be molten ionic compounds, and they also conduct electricity. Cations travel to the cathode, anions travel to the anode through the salt bridge or the U-tube, or we can also make this out of a porous boundary, porous cup. Okay, so let's navigate that. Let's find some cations. So in this solution, we have a whole bunch of copper 2+ cations. Okay, so those copper 2 pluses are going to try to get to this cathode stick. So the copper 2 pluses need to try to get to this cathode. So if they're going to go up through this electrolyte, and they're going to try to get there because they as well would love to pick up 2 electrons. Remember this, all these electrons, all these blue electrons that are coming in this stick, they would love to pick up those electrons. It's a weaker oxidizing agent, so it can't pick them up because the stronger silver ion picks them up, right? Move out of my way. I'm getting those donuts. So it gets this copper 2+ just kind of hangs out waiting for their turn, more copper 2 pluses hanging out waiting for their turn, more copper 2 pluses hanging out waiting for, that's why it's positively charged, because I've got all this positive density around this stick making that stick positively charged. Okay, so cations travel, oh, I've got another cation in here, right? I've got my sodium chlorides, so my sodiums are also making that journey, also hanging out here, also wanting to pick up an electron, but super weak, so they won't. So that's the flow of the anions, or cations, I mean. The flow of the anions, I'm running out of colors and space. I think I'm just going to erase this for a second to get a bit of, so you can see what's going on here. Let's just take these chloride ions in here. What kind of color should I use? Let's use this one. No, let's not use that one. Let's use this one. Okay, so my chloride ions are one of the anions. They're going to go to the anode. So here's a chloride ion eventually makes its way over here. It would love to give away its electron. Actually, it wouldn't. It's very stable as chloride, but it could give up its electron and become chlorine gas. But it waits its turn. It's certainly not the strongest reducing agent. Copper is, and so it would just hang out there, making this now negatively charged because I have all these chlorides hanging out there. And all of these nitrates that are in my solution as well, those nitrates, NO3 minuses, would also be coming over here, NO3 minuses, because they're also going to be reducing agents and, able to give away its electrons, but it won't. And so because I have this buildup of anions, negativeness at this post, that's why that ended up being a negative end of our battery. Okay, let's see another example. I think that example was long enough, so I'm going to get you to go into your notes package, and I want you to have a look at the examples that are in there under the answer key for the notes package.